Here we have a function z, and we can see that we have variables x, y, and w. And furthermore, x is a function of w and s, and y is a function of w. So in this example, the ultimate source of change in z comes from two sources, w, okay, and s. All right, so you are asked to calculate the partial total derivatives, z with respect to w and z with respect to s. All right, so we will start with this one here. And regardless of which one we start with, our starting point needs to be to set out the total differential, dz. Okay, so let's do that as a first step. All right, so you should be quite familiar with setting out the total differential at this point. Okay. So we'll start with this partial total derivative where we will allow w to change and we will be holding s constant. All right, so we need to now divide through by dw, but we are going to use the notation to indicate that what we are calculating here is a partial total derivative. Okay, so on this side, we need to indicate our partial total derivative like that. And on the right-hand side, we will need to use our partial derivative notation. Okay. So here we go. Instead of the d, we've got the curly d. W. dz. Okay, so now we need to go ahead and calculate partial derivative of z with respect to x. We're going to have 6x plus 4y. Okay. The partial derivative of x with respect to w, which will be 9. This one here, we're going to end up with 4x. This one here, we work with this function here, 10. And finally, partially differentiate. And that will, of course, be 1. All right, so we will end up with that there. Continuing now with the second part of the question, where we will now be examining the change in z, allowing s to change and holding w constant. So again, we are calculating a partial total derivative. So our first step would be this dz. All right, so that would be what we see here. And our next step is now to calculate this. So what we need to do is now divide through by the differential ds, but using the notation that indicates that we are calculating a partial total derivative. So let's do that down here. Okay. All right. And we would need to divide through not only the left-hand side, but also the right-hand side by ds, but using our partial notation as we did with w. All right, so let's do that down here. S plus All right, so we can go ahead now and calculate partial derivative of z with respect to x. Right. And here, the partial derivative of x with respect to s now. So we would end up with 6. Plus, working this out here, we would end up with 4x, and working now with this y function here, and we can see that there's no s term, so we would have 0 there. Okay, partially differentiating with respect to w, the z function with respect to w, we'd end up with 5, and then partially differentiating w with respect to s. Well, we can clearly see that there's no relationship between these two here, so this would also be 0, and our final answer would be as follows, because this term and this term would both equal 0.